Hello students, in this particular video we are going to learn the derivation of magnetic field which are produced by or created by a straight solenoid. So calculation of magnetic field, inside a long solenoid. The meaning of long solenoid we know from our previous video that the length of the solenoid will be very large as compared to its diameter. So we are assuming the magnetic field inside closely wound long solenoid is uniform everywhere. Let us write that point. The magnetic field inside a closely wound long solenoid is uniform everywhere. And zero outside. Many students may be thinking, why zero outside? So the magnetic field inside the solenoid is like they are closely spaced and they are parallel to each other, and they are able to create more number of field lines, therefore they are having larger value, but outside they are very weak, largely separated. So magnetic field outside the solenoid, practically it won't be zero, it will have some small values, but we are neglecting it as compared to inside inner part. The outer is having lesser value of magnetic field, so that's why we are ignoring that. Now let us draw the cross sectional view of a solenoid. Cross sectional view in the sense we are just trying to represent the dots and cross of the currents. Let us take first figure which I was explaining in the previous video, in which I have explained. I will try to draw that figure also here. This was our first figure. So this is how we kept the turns copper wire. So current is flowing through these adjoining turns like this. So if we grasp this solenoid in our right hand, this will become north pole, this will become south pole. So here at the bottom layer the current is entering, so draw cross, and at the top layer the current is coming out of the plane of the paper, so dot. These are currents, cross and dots are representing current, and the magnetic field is getting produced inside. We are assuming uniform magnetic field at each and every point, and outside we have taken it zero. Now this is the direction of magnetic field inside the loop, so definitely this is south pole, this is north pole. Now in order to find the magnetic field, this figure we call the cross sectional magnetic field of a long solenoid, and this is cross sectional view. Okay, of magnetic field. So or cross sectional view of the solenoid with the representation of magnetic field. So to determine magnetic field at any point, first of all we have to consider a Amperian loop. We are going to apply the Ampere circuital law to determine the magnetic field due to a long straight solenoid. So for that, as you know, that to apply Ampere circuital law, we need to consider Amperian loop. Let us consider one Amperian loop here. So this is the Amperian loop we are going to consider at this point. Let us take the length of this Ampere, first name it A, B, C and D, and let us say the length of this Amperian loop as L, and this loop is in this way, in this direction. This is how we have considered this loop, and length of the loop is L. So now let us write one point. To determine magnetic field, B at any inside point, at any inside point, consider a rectangular closed path ABCD as Amperian loop. So now it's easy. Then according to Ampere circuital law, we can write according to Ampere's circuital law, Ampere's circuital law, we know that closed line integral B dot dl will be equal to mu naught times the total current enclosed by the loop, total current through the loop ABCD. So this part is very important, B dot dl. Always remember, whenever we are finding this loop, so this loop is having four parts A, B, B, C, C, D and D A. So if you take B dot dl along this length AB, so dl vector will be pointing in this direction, B vector is also in the same direction. So theta 1 will be 0, theta will be 0 degree here. Now, so one by one we are going to, so closed line integral, it will be line integral B dot dl from A to B, and here we don't write close because it is open line. If we join all together, then we are getting closed loop. Okay, so A to B and then B to C, this is also open, B dot dl, and then C to D, that is also open, and D to A, that is also open individually. If you join all, then we are getting closed loop, that is ABCD, and that we want. So we need to calculate all individually. So A to B, if we are going to observe B dot dl, so angle between B and dl is 0 degree. So this angle is, let us so call theta 1. So B dl cos 0 degree, and B is constant, so it will be out of the integration, and cos 0 degree it is 1. Integration of dl will be equal to L only, and length of the solenoid is L only. Sorry, not length of the solenoid, length of this loop, we have taken it as L. Now from B to C, again we have to do the same part, A to B then B to C. You can see, all my dear student, from B to C, if you take dl vector, it is pointing in this direction and magnetic field is in this direction. So here theta is equal to 90 degree. And if you take dot product of this, so cos theta is cos 90 degree, which is 0. So directly we can say the magnetic field is going to be this contribution of this particular B dot dl of this part will be 0. Now A to B, B to C, and then C to D, B dot dl. So it is outside the loop. B dl cos theta. So outside the loop, we have already said that the magnetic field is 0. Okay. So if magnetic field itself is 0, so B dl cos theta, and theta in this case is dl element is pointing in this direction and B vector is, if it is there, but B vector is not there, B is already 0. So if one is 0, another is non-zero, if you take the dot product, that is 0 only. So no question of writing theta and all if B value is 0 there. So directly we can put it 0, and then D to A, B dot dl. So B dl cos theta. So from D to A, dl vector is pointing in this direction, B vector is pointing in this direction. So again theta is equal to 90 degree for this case. So it is B dl cos 90 degree, which is equal to 0. So finally, if we call this one as first equation, put all the values, then this is BL, this is 0, this is 0, this is 0. So finally we got closed line integral of B dl over this loop ABCD is equal to B into L. Now second part is, what is this L representing? L is representing length of the side AB of the rectangular loop ABCD. Length of side AB of closed loop ABCD. Now we are going to define, let small n be the number of turns per unit length. Okay. Let number of turns per unit length, number of turns per unit length of solenoid equal to small n. What is the meaning of that? In unit length, how many turns are there? So if we have L length, in unit length n number of turns, so in L length, total number of turns in length L of the solenoid. So total number of turns in length L of solenoid will be equal to n into L, and in each turn the current is I. The current which is flowing is I. You see, this is the current I which is flowing through each turn. So what is the total current that is going to be enclosed? It is N into L into I. So total current through the loop ABCD will be, in one turn it's I and these many turns. So N into L into I these many amperes of current. And now according to Ampere's circuital law, according to Ampere's circuital law, we can write B dot dl is equal to mu naught into current enclosed. So B dot dl, we already got BL, and mu naught, and current enclosed is NLI. So this L will cancel from both the side. So B value will become mu naught into N into I, where small n representing the number of turns per unit length of the solenoid. So n can be written as n by L also, where n is representing total number of turns and L is representing length of the solenoid. Okay, so mu naught into N into I. So if this derivation comes in your exam, you need to derive it. You have to write up to this, and you have to draw the diagram like this only. And if you do like this, then you will get full marks. Okay, so at least when you write your exam, you first draw this cross sectional view. This diagram also, if you want, you can draw it. And then this B dot dl through ABCD, split in 4 parts, quickly get BL, and NLI, equate it, get the value of magnetic field. So this completes the derivation of solenoid magnetic field due to a straight solenoid. Thank you.